Welcome again, ladies and gents, to another flipped lesson. Today our focus is on reviewing how to do heat stoich and also understanding how we actually get these delta H numbers for a chemical reaction. So let's start by reviewing how we do heat stoich. We learned yesterday in the video that the tie to the kilojoules in a chemical reaction is all about the coefficients, because what that tells us is how many moles we either need to put in or produce for an associated heat change. So if we look at the problem that we're solving for this guy here in the Google form, I wanted to know how much heat I can make when I react 32 grams of aluminum. So I want to use my aluminum piece to my energy. So what this tells me is that for every 2 moles of aluminum that I put in, I can make 144 kilojoules of energy. So if I look at where I'm starting in the problem, I've got mass. So in this problem, I'm going from mass to moles to heat. So it's a two-step problem. So I want to know how many kilojoules I can make when I react 32.0 grams of aluminum. So in order for me to use my heat, I have to turn my grams of aluminum into moles. So I'd look at the periodic table to get the molar mass of aluminum, which is 26.982. That's grams of aluminum for every 1 mole. My grams cancel, I'm now in moles, so I can use my associated energy change, because what this reaction tells me is that for every 2 moles of aluminum that I react, I can produce 144 kilojoules of energy. So in my calculator, I'll multiply 32 times negative 144, and I'll divide by the product of 26.982 times 2. Because this guy has 3 sig figs to start, I'm going to need 3 sig figs in my answer. So that's going to give me an answer of negative 76.6 kilojoules, and hopefully that's what you all got last night when you tried this problem. So this tells me that for when every 32 grams of aluminum I put into the reaction, I can make 67.6 kilojoules in that process. But how exactly do we get this delta H number? That's going to be our focus for the video today. But before we get started, we've seen this delta H guy a lot. We've seen it in delta H fusion when we melt stuff. We've seen delta H vaporization when we evaporate stuff. And we're going to learn that we can see it in terms of delta H cum, which just means combustion, or delta H reaction, which means the enthalpy change for a reaction. But when it comes down to it at the end of the day, delta H is just another way for us to represent the flow of heat or energy in chemistry. And so that's what you kind of want to primarily focus on. Now, do we want to know the differences between all these different delta H's? Absolutely. But the number one thing you want to keep in mind is it's just another way for us to track where the energy is going based on a heat change. So what we're going to focus on now is how we actually get these numbers for a chemical reaction. We call this using standard heats of formation, and this covers pages 537 to 541 in your textbook. So when we're getting the delta H for a chemical reaction, it all starts by using this little guy here. What this little guy is he's called the standard heat of formation, and what he tells us is it's the amount of energy that is either needed or produced when you are making a compound from its elements in their standard states at 25 degrees Celsius and 1 atmosphere. So what that means is if I wanted to figure out what the standard heat of formation is for sodium chloride, I would react solid sodium with chlorine gas to produce my sodium chloride solid. Any heat change that is associated with this chemical reaction is what I would then define as the standard heat of formation of my sodium chloride. Now, why can we do that? Scientists have decided that free elements are going to have a delta H of 0. So what that means is when I think about my sodium and my chlorine going in to make my sodium chloride, because we define this as having no enthalpy, and this as having no enthalpy, any heat produced or absorbed by the reaction has to be because of this compound. So it's a way for us to go ahead and define a delta H value for any compound that we can make. So things that are free elements are going to be things that stand alone. So solid sodium, any of our Hankelbrief or Hofbrinkel, as Mrs. Staub likes to say, elements. All of those things would have a delta H sub F of 0. All the other delta H numbers you could possibly need have been calculated for you and can be found in the table on page 975 in your textbook. So at the end of the video, I'm going to ask you to try a problem. So if you don't have your textbook with you, go ahead to the back of the room and grab one because you'll need that table on page 975 at the end. So how we calculate the delta H for a reaction is by using the summation equation. So these big fancy schmancy sigma signs just mean summation. So what this tells us is the enthalpy change for a reaction is going to be because of the total energy of the products divided by the total enthalpy of the reactants. And if we think about this in terms of endothermic and exothermic, it makes a little bit of sense. We know that if we have an overall delta H that is positive, what that tells us is that the delta H of our products has to be greater than the delta H of our reactants. Because if we think about our reaction coordinates, in order for us to have an endothermic process, we have to put energy in. So our products have to end up with a higher energy value than our reactants started with. So that would mean that this number has to be numerically greater than our reactant number. If we think about an exothermic reaction that has a negative delta H value, this means that the delta H of your products would have to be less than the delta H of your reactants in order for your energy to be produced. So the number on the product side would have to be lower than the number on the reactant side in order for us to have that negative energy change for the reaction. So this summation equation just helps us define whether we have something endothermic or exothermic. So let's do an example. What we're going to do is we're going to focus on calculating the enthalpy change for the formation of carbon dioxide. So in that reaction, we put in oxygen gas and carbon monoxide to make carbon dioxide. So our delta H of the reaction is going to be the sum of our products minus the sum of our reactants. So what we want to do is we want to go on page 975 in our textbook and find the numbers for each of these reactants. So if we look in our text, we'll find the delta H of O2 is 0 kilojoules per mole, which should make sense because we already know that your Hankel-Briffs and free elements have a delta H of 0. The delta H of carbon monoxide is found in your textbook to be negative 110.5 kilojoules per mole. And the delta H of carbon dioxide in your textbook is found to be negative 393.5 kilojoules per mole. So if we think about these units, they're super, super important because what they tell us is the amount of energy we need for each mole of our compound that we're dealing with. So when we look at a chemical reaction, we'll have coefficients. What those coefficients tell us is how many moles of that substance are actually reacting. So when you're doing your summation equation, you need to take your coefficients into consideration because if it's greater than 1, you have to multiply this number by the coefficient. So let's go ahead and let's calculate this problem. So we know the delta H for this reaction is going to be equal to the summation of your products. Well, in this case, it's easy because there's only one product. So since there's 2 of our carbon dioxides, we just have to take the number we found in our textbook and multiply it by 2. And we're going to subtract from that number, because O2 is 0, we don't have to worry about it, our carbon monoxide. Since there's 2 of them again, we would do 2 times negative 110.5. So we can go ahead and enter this in our calculator. We do 2 times the heat of our carbon dioxide minus 2 times the heat of our carbon monoxide. So if you've done that correctly in your calculator, you should get a numerical answer of negative 566 kilojoules. So what that tells us is the enthalpy change for this reaction is negative 566 kilojoules. So if we were doing some sort of other stoichiometry problem now, because let's say we didn't put a mole of O2 in, let's say we had 300 grams, we could figure out how much energy we could get by the combustion of that oxygen, just like we did in yesterday's video. So what I'd like you guys to do is go ahead and try this guy here using page 975 in your textbook. If you do this correctly, you should get an answer of negative 1,398 kilojoules. So go ahead and give this guy a shot. If you've got any questions, I'll be taking them at the beginning of class tomorrow, or you can always email me. Have a great night, guys.